chapter 15.1 now. It's a new chapter, 15. And we're moving away from partial derivatives. And we're going to now look at integration. The first type of integration we're going to look at is double integrals over rectangles. So a generic version of how that question would be written would look something like this. Not a single integral, but a double integral, with two integral signs, over some two-dimensional region R of a function containing both x's and y's, dA. And dA is a placeholder for dx dy or dy dx. They're both exactly the same. But dA can also be used if we use polar coordinate system, in which case this will change into drs and dθs. And that's all you typically have, either Cartesian or polar. And R is, in this section, 15.1 at least, R is a region in the xy plane. And it's typically going to be a rectangle. Now, if you're interested in knowing what do I find when I get this, because I'm going to get an answer and it will be a number, right? It'll be 42 or 0 or whatever it may choose to be. And so here goes. I want you to imagine that on the floor, you have your rectangular plane, right? So it's that guy. This fella in here is R. And you have a function above it. So for every value of x and y, there's a value called f of x, y, the z coordinate. And let's say that this region, you know, kind of looks like that, right? So that's basically, you know, z equals that guy. If you imagine this point, it will get to there. Imagine the origin, maybe it will get to here. Imagine this one, it will get to here. Imagine this one, it might get to here. And what you're going to have is a kind of curvy surface that looks like this. And that box with a curved top to it, right? So it's not just a rectangle, but it starts off as a cuboid, right? It goes up just like a cuboid. But when it meets that surface, can you imagine someone with a knife curving the top off, right? Carving the top off, but in a curved-like way, right? The volume of that block, that's the best word I can think, is what this is equal to. So if you're wondering, what am I calculating when I get a double integral? One of the most common ways to think about it is I'm finding the volume of this block. So R is on the floor, right? 0 to 1, 0 to 7 for y's. Going upwards, meeting the surface Z at different heights, right? Because at one place it's quite low and the other it's high. And that red block, its volume, is equal to that double integral. Let's show you how it works then. Suppose I want to find the double integral over a region R of x squared plus xy. And I want to do dA. And R is described as x goes from 0 to 2 and y goes from 1 to 3, right? So this is region R. The double integral would look something like this. You can either do x dx followed by dy, or you can do dy followed by dx. I'm going to choose to do dx dy. So I'm replacing this by that guy. Now, since x is first, the range of x is from 0 to 2. And since y is last, the region for y is 1 to 3. And that's how you would typically write down this integral using the extra information. So let's figure out how you do it. I'm doing this a lot slower and with a lot more lines than you typically would ever do. You essentially do two integrals. The first integral you do is with respect to x, and we are going to have to do partial integration. Okay, so this is going to be from x equals 0 to x equals 2, right? And now I need to integrate this expression with respect to x. So we are integrating, right? Maggie, you got your integration hat on. X squared. Add 1 to the power and divide by the new power. Now you've done enough partial differentiation in your life that you should be able to make a pretty decent guess at how you do partial integration. What is the integral of xy with respect to x?
1/2 x squared.
Anything else?
Y.
Don't you just treat y as a constant? So it's like integrating 5x, right, or 10x, right? So it's a 1/2 x squared y. Isn't that the same kind of thing that you do with differentiation? Don't you pretend the other variable is a number, right, a constant? Now, in this case, then, you plug in 2 and you get 1/3 times 2 cubed plus 1/2 2 squared y minus, well, when you plug in zeros, you just get a whole load of zeros. And now you've got 8/3 plus, I believe it's 2y dy. Are you comfortable so far? Does that make sense what we've been doing here? Okay, now isn't that also just a normal calc 2 integral? So I'll do it over here. So we've got the integral from 1 to 3 of 8/3 plus 2y dy. And you integrate 8/3 with respect to y, and you integrate 2y with respect to y, and then you evaluate it at y equals 1 to y equals 3. And so you're going to get 8/3 times 3 plus 3 squared. Take away 8/3 times 1 plus 1 squared. And what's that? 8 and 9, that's 17. 1 and 8/3 gets you 11/3. 51/3, take away 11, I believe the answer is 40/3. So this double integral is the number 40/3. Anything about that process that you're not comfortable with, you want me to talk about? I'm not getting a lot of feedback here. There's not enough people with pictures on so I can see your faces. Okay, I'll put you in the spot. Harrison, are you cool with this and you're allowed to say no?
I think I am. I think
Okay.
This makes sense.
Okay, then that's it. Christian, are you cool with this?
Yeah, it's always going to be 1023, right? It's never going to change for double integrations.
These numbers,
Yeah,
they'll change every time.
got
Next
it.
time it'll be 0, 20, 5, 11, right?
I was hoping it wouldn't, but okay.
Okay, you were asking a lot there, not to change the numbers. Right. Now I'm going to show you a slight change to notation that I prefer to do. Do you know how these are numbers and these are numbers and these are variables? And it's very often the case, especially when the double integrals get uglier and uglier and the expressions are not numbers, which is probably going to not happen in this section, but in the next one, right, in 5.2. I find it more helpful to do the following. So I'm going to show you a question where I change the notation a little bit. I'm not changing this. That's just the basic building block. R this time is going to be x goes from 0 to 2 and y goes from 0 to 1, right? And we're going to be asked to find the integral of x cubed plus xy squared. And we're going to do a dx and we're going to do a dy because we can do any one of the two that we like, but the change in notation. I find it helpful to put not 0 to 2, but x is 0 to x equals 2, and not 0 to 1, but y equals 0 and to y equals 1. Do you see that just makes it a lot clearer which number belongs to which letter of the alphabet, right? Which variable. That's really the only reason I'm doing it. So in this case, it's going to be the integral from y equals 0 to 1. That's that guy. And this guy gets done first. Well, that's 1/4 x to the 4 plus 1/2 x squared y squared. Evaluated at, see, x equals 0 to x equals 2. Then that flow nicely. See what I'm getting at? With the 0 and the 2 again. Right, let's check this integration, make sure we're comfortable. Isn't this the power rule from Calc 2? Add 1 to the power, divide by the new power. Isn't this also the power rule? And y squared is just like a constant, right? It doesn't go anywhere, it just gets put here. So far, so good? Right, now, evaluating this fella, you're going to get 1/4 2 to the 4 plus 1/2 2 squared y squared. Take away a whole lot of nothings. So we now have the integral y equals 0 to y equals 1. And that guy gets you 4, and that guy gets you 2y squared. Okay, so far so good. Right, now, Calc 2, integration. Oops, don't need that. 4 gets you 4y. Add 1 to the power, divide by the new power gets you that guy. Evaluated from 0 to 1. You get 4 lots of 1 plus 2/3 times 1 cubed. Take away a whole load of zeros again. And that's 4 and 2/3. And that's 12 and 2. I make that 14/3. So the answer to that one is 14/3. How are we doing, guys? So far, so good? Right. Let's just up the ante a little bit each time, not doing too much to confuse the issue. Let's find a double integral over some region R, and the function is going to be sine x sine y plus e to the x plus 2. And we're going to do dx dy, and the region R is going to be from x equals 0 to pi, and y is going to be from 0 to ½ pi. So my integral is going to be y equals 0 to y equals pi upon 2, x equals 0 to x equals pi, this expression. Okay, if you want to integrate this guy with respect to x, then you have to be careful because, you know, if you see a y, treat it like a constant. So this guy here, what do you get if you integrate sine x sine y? Is it plus or minus? Start with that.
Minus.
Minus. Would you agree it's a cosine x times a sine y? Are you comfortable about that sine y still being sine y? So far, so good. Right? Now, what is e to the x? Well, let's not insult your intelligence. It's e to the x. Now, what will the number 2 get us?
2x.
2x. Again, I'm insulting your intelligence, right? So we'll now do x equals 0 to x equals pi. 0 is a really nice number to have in one of these because it tends to reduce, what the thing looks like. So you plug in pi, you're going to have negative the cosine of pi times sine y plus e to the pi plus 2 pi. So far, so good. But it is not, and I'll repeat that, it's not take away 0 this time. It's take away negative the cosine of 0 sine y plus e to the 0 plus 2 lots of 0. And you see that 2 of these terms aren't 0 this time, right? They actually are things. So let's see what we get. With the integral from y equals 0 to pi upon 2. What's the cosine of pi? What number is the cosine of pi?
-1.
So 2 negatives make it a positive, so that guy gets you sine y. E to the pi is just an ugly number, so it's e to the pi. 2 pi is just a number. Now, what's the cosine of 0? What number is the cosine of 0?
1.
So that's -1, but then you're going to subtract it, so you get a plus. One of those. Isn't that 1? Take away 1. Are you comfortable about the pieces that we've got? Why the first piece is plus sine y, but the second piece, why it ends up just being -1, right? You're subtracting this answer and you're subtracting a 1. And this particular combination ends up being positive because you're subtracting a negative, and that makes it positive 1 times sine y. Now, in this case, you're going to now integrate with respect to y, and you get that guy. Okay, what do you get if you integrate e to the pi? And do not make your life difficult. With respect to y, what do you get when you integrate e to the pi?
E to the pi y.
And for the same argument, won't you get 2 pi y for the other guy? And if I'd been clever, wouldn't I have noticed that this sine y and that sine y gave me 2 sine y's? In which case, won't I get -2 over there? So I don't need to, spend a lot of time. So sine y plus sine y is 2 sine y's. And when you integrate 2 sine y's, you get this term here. And the only number I've missed was -1, but isn't -1 negative y? And now we evaluate them at these 2 points. So it's -2 cosine of pi plus e to the pi times pi plus 2 pi times pi, take away a pi.
Isn't
Subtract-
that pi over 2?
Which one have I not got a 2 on? Pi over 2.
Isn't it? pi
Oh,
over
this here,
2?
thank you. It is pi upon
Okay.
2. So that's e to the pi, this is pi upon 2. And this guy is pi upon 2, and this guy is also pi upon 2. Take away zeros, so I get -2 cosine of 0 plus e to the pi times nothing plus 2 pi nothing, take away nothing. Okay, so that basically is first guy, take away second guy. Right, cosine of pi upon 2, isn't that 0? So this disappears. And this guy is still here, so pi upon 2 e to the pi. 2's cancel and I get add a pi squared. This gets me pi upon 2. Cosine of 0 is 1, so this is -2, but subtracting a -2 gave me a +2, and barring accidents, isn't that the final answer? Are you feeling a little bit more comfortable about double integrals when we're using rectangular regions for R? Now, only because I'm a creature of habit, do you notice I'm doing the X and then the Y? I'm not going to do it, but you could have done it Y and X, right? You could have said dy dx. Now, if you do that, don't you have to make sure that you switch these integrals? And can you just trust me, because I'm not doing it, that you'll get exactly that answer? And there might be some situations that when you look at it, you say to yourself, you know, if I do this with the Y's first and then the X is second, it's easier, right? The order might make it slightly easier. Can you remember doing partial derivatives, and sometimes it was better to do the X's before you did the Y's? It won't be quite as good as that, right? But there will be, I'm sure, some situations where you just look at something and say, yeah, I think I'm going to do it X's as opposed to Y's. Now, the next question is a lot easier in a lot of ways because you don't have any choice. And I'm going to put my change in notation, where I actually, in their case, they just said 1, 7 and 1, 9, right? That's what it looked like in WebAssign, right? 1 and 7, 1 and 9. So they've decided to do this with a Y first and then an X second, which is fine. So I'm going to put a little bracket around that guy just to emphasize that we need to do this one first. So I'm going to do an X equals 1 to X equals 9 here. Whatever it is, it's going to happen there, and then a dx. So now I forget about that. And I just focus on what's in front of us. I'm going to do that in the side here. I want you to think of that X as 42, right? It's just a number. So in a lot of ways, just ignore it. What technique from Calc 2 am I going to use to integrate that ugly fraction?
U substitution.
And what is the U sub going to be? You're correct. What's the U sub going to be? Anybody want to help them up? What's the U sub going to be?
Y.
Didn't quite catch what you said, Matthew. Is that what you said?
Yep.
Okay, you picked the right one. Would you agree making it Y? I've never done a U sub in the world where the letter you started with was ever going to do any good, right? So you never do a U sub, U equals X, or U equals Y, or U, it doesn't work, right? It doesn't do anything. Now, to remind you, and we get a bit rusty when we don't do things for well, at least the way I set it up, don't you differentiate with respect to Y, and you get 1 over Y, and then you do a little crossover. In this particular case, I don't need to isolate the dy, isn't it already isolated when I did the cross and multiply? So I now know that dy is going to be this fella. So we're going to get u, that's log y, over xy, and instead of dy, we're going to have y du. And that means that cancel, cancel, we're going to have u over x du. Now, if this X on the bottom is freaking you out a little bit, will you think of it as U over 42 again? Right? It's just a number. If it really bugs you, do you know you can bring it outside the integral and call it that? Does that help your mind see it as not important for the process? Right? Now you integrate u, you will get a half u squared. Great. And I'll keep that 1 over x out the way. And that becomes 1/2 the natural log of y squared. Are we cool about returning back to the original variable? And then to make it look at least presentable, can't I return it so that everything's kind of together as one fraction? Right? So the 2 and the x become 2x in the bottom. So I can now return and say, oh, so you want me to do the natural log of y squared all over 2x, evaluated at y equals 1 and y equals 7. So evidently I didn't need that much room. So it's going to be from x equals 1 to x equals 9. Right, let's plug it in. If you put in 7, you get the natural log of 7 squared over 2x. Take away the natural log of 1 squared over 2x dx. Okay, that is just a number, and I'll live with that. What is the natural log of 1 as a number? Because it's a very interesting number. Natural log of 1.
Isn't it
Zero.
0?
Yeah, so basically doesn't all this disappear? So we are now looking at the natural log of 7 squared over 2x dx. Now, if numbers like that and fractions like that bug you, you are allowed to just pull them outside and just integrate the bare bones. Are you happy about this becoming that? Would you agree that for a lot of you anyway, isn't this much easier to see as far as integration goes than trying to deal with this, right? Because you end up doing weird chain rule things that you probably shouldn't do, right? In this case, would you agree the answer is just log of x? So it's the natural log of 7 squared over 2 times the natural log of x evaluated at x equals 1 to x equals 9. So I have the natural log of 7 squared over 2 times the natural log of 9, take away the natural log of 1. But I know that's 0, so all you get left with is that. And so natural log of 9, natural log of 7 squared all over 2. It's still a double integral, but would you agree they're getting uglier and uglier as far as the integration part goes, right? In this case, I had to do a u sub, and we had to deal with some really weird looking answer, but I'm checking that, and that was exactly the answer they've got, so I know it's right. Any questions about that one before we move on to our next one? Looking good? Okay, I like looking good. There are just so many different flavors and types. It's kind of hard to pick things that are different, or not different, but you know, have got something in them that's interesting because they're all kind of different. And this is a version of 8 then. They're going to do it from x equals 1 to x equals 64. And they're going to do it from y equals 1 to y equals 8. And they have an x over y plus y over x. And you're going to do the y and you're going to do the x. I'm only going to do the first piece. In other words, the integration that's here. Right, I'm just going to do that one. And then you could, you know, figure it out from there. With respect to y. Integrate x over y is integrating 42 over y, right? What is the integral of x over y then?
X ln y.
I can't catch what you're saying, Maggie. It might be right, I just didn't hear it.
Is
The
it
in-
x times the log of y?
It is. X times the natural log of y. Now, and am I agreeing with you? Because I should. I had to double check there. Y over x also looks like the other guy, but you notice that they're in the different place here, right? Now, y over x is not a log, right? When you integrate y over x, you do not get a log. I want you to think of this as like 1/42 y, right? Y over 42. Think of it like that. So isn't that a power rule? And so when you integrate that guy, you add 1 to the power, and then you divide by the new power. Are you happy about this guy and that guy and how they are different when you integrate with respect to y? Are you comfortable that's x log y and that's just add 1 to the power and divide by the new power? We're going to evaluate it at y equals 1 and 8. So you're going to plug in 8 and you're going to get natural log of 8 times x, or x log 8 if you like it that way. 64 over 2x. Take away x times the natural log of 1 plus 1 squared over 2x dx. Can't really do much about that. This can simplify a little bit. That's 0, so don't care what it is. And that's 1 over 2x, so you're going to take it away. Right. Do you see that what you've got now is really just a Calc 2 integration? Right. That's just a horrible decimal. So won't that be the power rule? Won't that be a log? And if you call that minus a half 1 over x, so if you call this guy minus 1/2 1 over x, isn't it easier to see what its integral is? Sometimes it's better to write it slightly differently to make the integral easier to see. And that's the guy that you're going to do. And I'll do my ... which means, you know, and finish it off in your own time. See what I can do. Question 9. It's going to be the integral from 0 to 1 to 0 to pi upon 2 of t squared sine cubed theta d theta dt. And now I'm going to show you a nice trick. This only works when these are rectangles. In other words, when these are both numbers, you can do this. Some expressions, not that one, but this one, are really made up of 2 different functions multiplied together. One of them with t's in it, and the other with thetas. And we call these situations variable separable, just like from DE, right? And when you are variable separable, you are allowed to do the following. Isn't that nice that you can separate a double integral as the multiplication of 2 separate integrals? Now, this is allowed because, would you agree, this one has nothing but t's in it, and this one has nothing but thetas in it, right? So they are separable. Can you see why you couldn't do it to this one, right? There's no way of separating these out. And if I got any of the other ones handy. Do you know I could have separated this one? Right? If I wanted to, wouldn't this be 1 over x dx and log y over y, right? I could have separated that one. So If you can separate them, I suggest strongly that you do so, because it just tends to make your work a lot easier. Now, this guy is a power rule. Add 1 to the power, divide by the new power, evaluate at t equals 0 to t equals 1. So that's going to be 1/3 times 1 cubed, take away nothing. So the first piece ends up being 1/3. And then you do this one totally separately. But I'm not going to do this one much further. Don't want to give away too much of the good stuff. How are you going to integrate sine cubed theta? Any suggestions? How to integrate? See?
Isn't it a chain rule? Like, would you pull the cubed sign out and make it a quantity cube? And then just do the chain rule?
Only if you were differentiation. But it
Oh,
won't work for integration. I know what you're saying. Yeah, it won't work, but it's good thinking. I like thinking.
This is more or less a guess, but aren't we taking the u sub of sine of theta and then splitting it into 2 separate trig functions?
I see some nods amongst you. Yes. So let me set it up for you. You're going to set it up by splitting it like that. And then you are going to do just a little bit more work on it. Sine squared theta is going to be called 1 take away cos squared theta. Is this beginning to ring some bells from Calc 2? And I think someone mentioned it. Aren't you going to have to do a U sub now? What would be the U sub that would get you out of this hole? Be careful. Don't make it too ugly. It's very simple U sub. You may have said it. I didn't catch it.
Cosine theta.
It's cosine theta. And can you trust me? It's going to take you a while, but eventually it'll work. And I'm making this answer up. Suppose the answer is 42. Won't the answer be 1/3 times 42? If the answer is 0, well, 1/3 times 0 is 0, right? Whatever this is, and it will be a number if you do it correctly, you go 1/3 times whatever this number is, and that's your final answer. So there is a haven't seen it in ages situation. Let's show you a question now that cannot be separated. In fact, this is going to be the last one for today. We're going to do the integral from x equals 0 to x equals 1, and from y equals 0 to y equals 1. And we're going to do 9xy, the square root of x squared plus y squared, and then it goes dy, and then it goes dx. Now, this cannot be separated, and it's the square root of x squared plus y squared that screws it up. See, if that was missing, couldn't you separate 9xy? That would be a very easy separation, right? You know, give the first one 9x and give the other integral just y. That would work. But since this is here, that's not going to happen. So we need to figure out how we are going to integrate this horrible mess. Okay, any suggestions about how you would integrate with respect to y this? And think of x as 42s or 1s or something. How would you integrate it?
I'd start by taking the use of what's being square rooted, so x squared plus y squared.
Good start. That's exactly what you do. Right. That's clearly the problem, right? And if you see a problem, well, I'm putting a percentage here. 80% of the time, isn't that going to be solved by a U sub? And then maybe an integration by parts or something for the other situations, or an X sub perhaps. So I'm differentiating with respect to y, but you remember who the variable is. So that guy's nothing. So all you get is 2y. You happy about the derivative is 2y? The crossover. And then divide both sides by 2y to isolate the dy. So switching spaces, I like to write on the right hand side because that's where my good eye is. So it's going to be the integral from 0 to 1. And the integral of 9 x y, the square root of u, 1 over 2y du. Okay, that y cancels with that y. I have a 9, an x, and a 2 unaccounted for, and a square root of u. So I'm going to do this. Have you noticed that I've pulled the 9 and the 2 out? Most people are comfortable about pulling a constant out of an integral. But in this context, isn't x a constant? So I can even pull out the x. Doesn't it make this integral a little bit cleaner to deal with? Right? If you left all the pieces of the x's and things, and that might distract you. So we're going to do x equals 0 to x equals 1. That guy. The integral of u to the half. Du. Then the power rule. Add 1 to the power and divide by the new power, which is that guy. That's a dx, by the way. And then return to the original variable. And u to the 3 over 2 is the square root of x squared plus y squared cubed, evaluated at y equals 0 to y equals 1. And we've got that guy. I'm going to make that a little bit prettier before I continue. That and that and that and that. A lot of cancelling, actually. You get 3x. The square root of x squared plus y squared cubed, evaluated at y equals 0 and y equals 1. So we can handle that. If you plug in y, you get 3x times the square root of x squared plus 1 squared cubed. Take away, if you plug in 0, you get 3x square root of x squared cubed dx. Can't really do much with that, so I'm not going to even attempt to do anything with it. X squared cubed is x to the 6. The square root of x to the 6 is x cubed. X times x cubed. Wow, that actually, that guy comes out quite nice. Are you comfortable with all the kind of did it in my head here? X to the 6, square root of x6 is x cubed times some more x, that guy. So we are now into one last integral, calc 2. This guy is a power rule. This guy's a mess. This guy, I'm going to have to call it that guy. Okay, what technique am I going to use to integrate this ugly expression?
Is it a product rule?
That's differentiation, Cap.
Could you use u sub?
You could. What would your u sub be?
X squared plus 1.
Yeah. Can you trust me that eventually it works with some ugly fraction and you get the answer? And I don't have time and you're going to do it anyway. So ... and you're finished. So I think what we've learned today is that you have to be good at Calc 2. Right? You have to be aware of, you know, like the sine cube theta 1 and u subs and, you know, all those kind of power rules and derivatives of x over y and whatever, all those kind of pieces. We have to be good at Calc 2. And that's true. You're going to have to be good at Calc 2 for a lot of the next 3 or so weeks in particular. So, oh, don't give me that face, Christian. That's depressing. Oh, that's better, right? So get up to speed if you're not. And last name for attendance. Bye-bye. And I'll hang about for any questions. I'm not throwing anything away until you've gone, Maggie. So what's your question? You didn't have your cap on today, young man. You were wanting to differentiate everything in sight, weren't you?
Yeah, I guess.
Okay.
Sorry about that.
No.
Can I see the second page? I can't tell you what's on it because I honestly don't know. I just know there was a lot of green writing on it.
Okay.
I think it was when you wrote out the official rule.
It's gonna be. I don't have anything in green, so when I find it, I know it's probably the only one. No, no, still not. Still no. Still no. If nothing else, it'll be in the first 5 minutes of the video. Here it is. That guy. Is that what you're talking about? Oh, I don't know if you can see it. Right, here we go. That one?
Yeah.
Yeah. So what that is basically trying to describe as badly, no, you know, it's a horrible thing, but R is the floor, right? Your rectangle's on the floor, and then the floor gets projected upwards and it meets up with the surface Z that's curving. And so if you imagine the four corners, you don't end up with a box. What you end up is kind of, it starts off as a box, a cuboid, but at the top isn't it got a nice curved area to it. And what you're finding when you find the double integral over R of this situation is you're finding essentially the volume of that box. And it is okay to get negative numbers because all that means is that the volume is below the XY plane and not above it. And it's also okay to get 0. And 0 will happen if the volume above the XY plane is exactly balanced by the other part of the volume, which is below the XY plane. So you can imagine a shape where it's up here and then it's down here and the plus and the minus, you know, match perfectly. So just like in normal single integrals, double integrals can be positive, they can be negative, and they can be 0. So don't be scared if, you know, negative or zeros, for instance, happen. Now you can think of another way, just came to me, of what a double integral does. Can you imagine that you've got on the floor, right, the rectangle, just a rectangle. And at every point in that rectangle, there's a temperature. So this bit might be 20 and that's 30, right? And this is 35 and that's 45, right? So when you're doing a double integral, what you're basically doing is finding like the total amount of heat that's in the plate, right? So it's adding all the 35s and the 45s together and it's coming up with a number that might represent the total heat content of a flat plate, because the third number is essentially the Z value.